Hello friends, welcome in a lecture of Mechanics of Solid Subject. Myself, Mitesh Patel. I am a assistant professor in a mechanical department at a Dr. Subhas Technical Campus, Junagadh. Today's our lecture topic is a torsion. In this lecture, we discuss about the what is the torsion, twisting moment, torque, and effect of this torque, twisting moment, or torsion, and generated shear stress and how to find out the shear stress and the design of shaft according to against the twisting or shear stress to overcome that and according to stiffness or strength of shaft. Okay, so let's start the lecture. First we see that what is the torsion. Torsion is a word defined as a twisting moment of the body. Okay, now we see the torque, what is the twisting moment and turning moment. Okay, torque or turning moment or twisting moment. Simply if one object is there, then twisting to this object, then it's called the given the torque, or it's also called the turning moment, or it's called also twisting moment. Okay, so let's see that in detail. In factories and workshops, shaft is used to transmit energy from one end to another end. To transmit the energy, a turning force is applied either to the rim, pulley, key to the shaft. Okay, so transmit the power. The turning force is provided with the help of pulley or key to the shaft or to any other suitable point at the some distance from the axis of shaft. The moment of couple acting on the shaft is called the torque, turning moment and twisting moment. So what is the turning moment, twisting moment and torque? The moment of couple acting on the shaft is called the torque or turning moment or twisting moment. These two forces are twisting this shaft in this direction, in clockwise direction. Then this moment of this couple is called the torque, twisting moment or turning moment. Okay, so what is the torque or turning moment or twisting moment equation? It's the turning force into distance between them, perpendicular distance between these two forces. So force into 2r. Okay, so r is the radius of shaft, F is the turning force, and T is the torque. Okay, so turning force is applied to the shaft. So the couple is generated here. If the belt is there, then this rotate this. If the belt is here, if the belt is there, and this belt is rotate the shaft in this direction, so the twisting moment it's generated in this direction. Okay, and so the two twisting forces are there to twist the shaft. Okay, so what is the value of torque? Is the force into perpendicular distance between the two forces. So force into perpendicular distance is the 2r and force F. Okay, so F into 2r. F is the turning force to turning the shaft. Torque is a T and R is the radius of shaft. Okay, now what is the unit of torque or turning moment or twisting moment is a Newton into meter or Newton into mm or kilonewton into mm. Okay, clear? Now angle of twist. What is the angle of twist? When the shaft is subjected to torque or under the torque, under the twisting moment, point A on the surface of shaft comes to A dash position. The angle AOA at the center of shaft is called the angle of twist. Means consider the one point A on shaft, and given the twisting moment or turning moment, and this point is moved to the A dash due to the twisting or turning moment of shaft. So this particular angle and O is the center point. Now this angle AOA dash angle is called the angle of twist or twisting angle, is defined by theta. Okay, angle of twist. Okay, and it's measured in radian. Twisting angle or angle of twist. Clear? Now see the shear stress in shaft, and shear stress is defined by tau. Its sign is a tau. When shaft is subjected to the equal and opposite end couple whose axis coincide with the axis of shaft, then shaft is said to be pure tension. At any point in the section of shaft, stress will be induced. The stress is called the shear stress in the shaft. Here we see the figure. If we provide the opposite couples whose axis is coincide with the axis of shaft, whose axis is coincide with the axis of shaft, then pure torsion said to be in pure torsion, shaft said to be in pure tension at any point in section, then shaft stress will be induced. એટલે કે શાફ્ટ છે અહીંયા કપલ એપ્લાય થાય છે, બરોબર છે, અને any axis will be coincide with the axis of shaft, then shaft should be in pure tension, pure torsion, and then any section of this shaft, the stress is generated. This stress is called the shear stress. Okay. Now strength of shaft. Shaft is transmitting the power, so maximum torque or power of shaft can be transmitted from the pulley to another is called the strength of shaft. So strength of shaft is defined by the maximum torque or power should be transmitted by the shaft. According to that, we define the strength of shaft. Okay. So two types of strength of shaft are there. Solid shaft and hollow shaft. Two shafts are there, and for that we have a directly equations. This equation is derived from in the designing of shaft, so we can directly use this equation of maximum torque. Maximum torque transmitted by the shaft is a torque T is equal to pi by 60 into shear stress tau into d raised to cube. D is the diameter of shaft and tau is the shear stress generated or induced into the shaft. Okay, this equation is directly used. This equation is derived in the designing of shaft. Okay, and similarly in this torque equations, maximum torque transmitted to the shaft is for hollow shaft is pi by 60 into tau into d raised to 4 minus small d raised to 4 upon capital D. For hollow shaft, capital D is the outermost diameter and innermost diameter is a small d. Okay, so this is the two equations to find out the maximum torque transmitted to the shaft. Okay, now another thing is a polar moment of inertia. Polar moment of inertia. What is the polar moment of inertia? Just above this lecture, just this lecture, after in last lecture we already solved the examples and see the what is the moment of inertia. So you know that what is the moment of inertia, but here the polar moment of inertia, and we know that the perpendicular axis theorem. So in perpendicular axis theorem, what is that? What is that? If we find out the moment of inertia of perpendicular axis to the x-axis and y-y plane, so this moment of inertia about this perpendicular axis, this moment of inertia called the polar moment of inertia. So polar moment of inertia is nothing but the moment of inertia about the perpendicular axis to x-axis and y-axis, okay, which are making the plane. So we know that the polar moment of inertia is find out with the help of at the z-axis and with the help of perpendicular axis theorem. And what is the perpendicular axis theorem? Moment of inertia of perpendicular axis, it's called the polar moment of inertia, IZZ, and find out with the help of Ixx plus Iyy. Moment of inertia about x-axis plus moment of inertia about y-axis. And the polar moment of inertia is defined by J. Izz is defined by J. Now for shaft, polar moment of inertia is a we can find out that Ixx is a moment of inertia of shaft or circular section about x-axis or about y-axis is same, pi by 64 into d raised to 4. Okay, so pi by 64 d raised to 4 about x-axis and pi by 464 d raised to 4 for y-axis for a shaft. Now summation of it, so 2 is 2 pi by 64 into d raised to 4. So 64 into 2 34, 32 is remaining. So pi by 32 into d raised to 4 is the polar moment of inertia for circular section or for shaft. Okay. And for hollow shaft, polar moment of inertia is a pi by 32 capital D raised to 4 minus small d raised to 4. Capital D is the outermost diameter of shaft and small d is the innermost diameter of the shaft. Okay. Now polar section modulus. So what is the section modulus? We know that the natural axis, moment of inertia about natural axis upon distance of the extreme fiber from the CG. It's a section modulus. But here we have a polar section modulus. So moment of inertia about polar moment of inertia and distance of extreme fiber from the CG. This ratio is called the polar section modulus. Okay, so and this is defined by J upon Y. Y is the distance of extreme fiber from CG. Okay, or for shaft we can see that, or we can say that it's a radius, because for shaft the extreme fiber distance from CG is a radius. Okay, so for shaft Y is a R. So Z upon R is the polar section of modulus for the circular section or shaft section. Okay, so what is the polar modulus, polar section modulus for a solid and hollow shaft? Let's see that. Put the value of J, pi by 32 into d raised to 4, and radius is a d by 2, so d cancel, so d raised to 3 and 2 cancel out, so 16 is remain. Pi by 16 into d raised to 3 is the polar section modulus of shaft, pi by 16 into d raised to 3. And now here for hollow shaft, pi by 16 into d raised to 4 capital minus d raised to small d raised to 4 upon capital D. Okay, so this is the polar section modulus for a shaft cross section means the circular section and polar moment of inertia. Okay, clear that? Now we go for the torsion theory. First out we see the assumptions which are considered into the torsion theory. Okay, so what are the assumptions? Let's see that. First, the material of shaft is uniform throughout the length. The material of shaft is uniform throughout the length. Okay, the first assumption is there. The second assumption, twisting along the shaft is uniform. So in this assumption, the twisting is provided, then twisting of shaft is uniform throughout the length of shaft. The shaft is uniform circular section throughout the length. Shaft having a uniform circular section, not any changes in circular section. Cross section of shaft which are plane before twist and remain plane after twist. Okay, before and after twisting, the cross section of the shaft remains plane, not change the plane. It remains plane. Its assumptions are considered. Remains the plane. Okay, એટલે કે સ્ટ્રેટ પ્લેન જ રહેશે. any cross section, માની લો કે this is the shaft and you consider this cross section. If we test twisting this shaft, then this plane, this cross section is become flat plane, not any changing after twisting or before twisting. Okay, એટલે કે ટ્વિસ્ટિંગ કરીએ ત્યારે પણ આ ક્રોસ સેક્શન છે એ સ્ટ્રેટ પ્લેન જ રહેશે, એમાં કંઈ ચેન્જીસ આવશે નહીં, ટ્વિસ્ટિંગ આપો કે ન આપો. This is the assumption. All the radius which are straight before twisting remain straight after twisting. But obvious that if we consider that cross section is a flat plane, then radius become straight, which are straight before and after twisting. Okay, these are the assumptions which are considered into the torsion theories. So let's remember this. It's important that it's already asked into the GTU. So these assumptions, remember that the diameter of shaft is constant. Okay, the material is uniform, twisting of shaft along the length is uniform, and the cross section of the shaft is continuously flat plane after or before twisting. Okay, these are the assumptions torsion theory. Now we go for the torsion theory. The one example is here taken. The one end of the shaft is fixed at this plane and one end is open, free. Open means it's free, and now given the twisting moment as shown in figure, the A point becomes go to the A dash point. Okay, get the new position. A point is get the new position of A dash after given twisting. Okay, so let's see that. Consider the shaft fixed one end and subjected to torque at the other end. Torque is defined by T. Torque, length of shaft L, small l, capital R is the radius of shaft. As the result of torque, every cross section of the shaft will be subjected to the shear stress. Okay, line CA, this line CA on the surface of shaft will be deformed to CA dash after given a torque, and OA to OA dash. This line and these lines become here to OA dash and CA dash after given a twisting. So angle AOA dash theta in radian is called the angle of twist, and phi angle of ACA. This angle is defined by phi. Okay, this angle is defined by phi. Clear that? Now shear stress is defined in this way. If this rectangle section is there and if the force is given there, then if they achieving the new position, it's defined by this way. New position is defined by dotted. Then this angle is phi shear strain. Now shear strain strain is defined by the equations is a deformation per unit length or deformation per length, but here deformation is measured in shear action is measured in form of 5. So how to get the equation of shear strain? Shear strain is find out with the help of if initial point is A and after that is A dash, achieving the position A dash after giving this shear force F. Okay, so now what is the shear stress? So along this length is L, so shear stress 5 is defined by A dash, deformation upon length. Deformation is a dash. Okay, so deformation per length. Okay, so length is this length is L and deformation is AAL. So shear strain is defined by deformation upon length, and deformation is A to A dash. We know that A point before the twisting before the twisting point is at here, and after given the torque, the A point become A dash. A point get the position at A dash. So deformation is a dash and length of shaft is a small l. So now if we consider this triangle, and from that, or we can say that it's equal to tan phi. Okay, clear? And we can see from that triangle achieving the new position. This is the 5 and this is the A dash A, this is the 5, so tan phi is equal to opposite side to nearby side, so this is the L, or A dash upon L. So A dash upon L ratio is defined by tan phi. Okay, in this assumptions, according to this assumptions. Okay, this is the phi and A dash, and according to that tan phi is equal to deformation A, opposite side to nearby side is a L. Okay, so tan phi is equal to A dash upon L. So shear strain is equal to A deformation upon length, A dash upon L, and this defined by tan phi. If the in tan phi, if the phi value is very small, then tan phi is almost, tan phi is almost, value of tan phi is almost to 5. So we can write the 5 instead of tan phi. If the phi value is very small, so tan phi value is almost nearer to 5. So we can write the phi instead of tan phi. So here write the 5 instead of tan phi. Okay, so we have a 5 value, it's equal to A dash upon L. Now arc A dash, here the arc A dash is the length of arc is find out with the help of radius into theta, and the radius of arc is defined by capital R and theta. So length of A dash arc is a r theta, so phi is equal to r theta upon L. Okay, now what is the modulus of rigidity? Modulus of rigidity is the Newton, and it's the ratio of shear stress upon shear strain. Okay, modulus of rigidity is the shear stress upon shear strain. Okay, modulus of rigidity is the ratio of shear stress upon shear strain. And what is the shear stress? Tau, and shear stress is defined by phi. And modulus of rigidity sign is a capital C. Capital C is defined by, modulus of rigidity is defined by C or capital G. Capital C or capital G. In some book is defined by G, and C in some book is defined as a C. Okay. Here we can see defined by C, a modulus of rigidity. Shear stress is a tau and shear strain is a phi. So modulus rigidity is a shear stress upon shear strain. And now get the value of phi from these equations is a tau upon modulus of rigidity. So now we have two equations, two value of phi, equation 1 value and equation 2 value over there here. So comparing this both value of phi of equation 1 and equation 2, so r theta upon L and tau upon C. Okay, now interchanging the r and C, so C become the right side and r go to the left side. Okay, tau upon r is equal to C theta upon L, and this is defined by equation 3. Okay, now we know that for a solid shaft, maximum torque transmitted through the solid shaft equation is a maximum torque T is equal to pi by 16 into tau into d raised to cube, and from that we got the value of shear stress from this equation. So tau is equal to 16 goes to there, 16 into torque T upon pi into d raised to cube. Okay, so tau is equal to 16 into t upon pi into d raised to cube. So this tau value is put into the equation of 3. Okay, so 16 into t upon pi into d raised to cube value of shear stress is put into the equation of 3. Okay, now we rearrange the equation. So t upon pi by 16 d raised to 3 into r c theta l, and r is converted into the diameter, so it's a d by 2, so d raised to 4 and multiply by 16 and 32, so t upon pi by 32 into d raised to 4, and this is the value of polar moment of inertia, pi by 32 into d raised to 4. So polar moment of inertia is defined by j, so instead of pi by 32 into d raised to 4 we define the j, so t upon j c theta upon l. So this equation 5. Okay, and here c theta upon l is equal to tau upon r, and c theta l is equal to t upon j. So we can write here that these relations c theta upon l is equal to t upon j and tau upon r, c theta upon l. So this relation is called the torsional equations. Okay, this is the torsion theory. I hope that you very well understand all things related to torsion, what is the torsion, and mainly torsion is count for the transmitting elements or rotational transmission of rotational motion. So I hope you very well understand all things. So torsion is important for the transmitting element of rotational motion. Okay, so shaft is the most transmitting element, and so torsion of shaft is very important topic. So in this chapter we only study the torsion of shaft. Okay, so in next lecture we discuss about the and solve the examples related to shaft torsion. Okay, torsion of shaft. I hope you very well enjoying the video, and thank you for listening the video. Thanks. And now next topic is a power transmitted by the shaft. Power transmitted by the shaft. So power, to find out the power transmitted to the shaft is the equation, we know that very well, 2 pi nt upon 60 for watt or SI units, and if we have to find out in horsepower, then equation become P is equal to power P is equal to 2 pi nt upon 4500, and here capital N is the revolution per minute and T is the torque in Newton into meter, and for horsepower it's kg into meter. Okay, and now the second topic is a torsional rigidity. Let twisting moment T produce a twist theta radians in the length L. Let's consider that twisting moment torque or twisting moment T produce a twist theta radians in length L of shaft. Then we know that according to torsional theory, T upon J is equal to C theta upon L. C is a rigidity of shaft, theta is a angle of twist, L is the length of shaft, T is the torque or twisting moment, and J is the polar moment of inertia of shaft. Okay, now angle of twist is theta is equal to TL upon Cj according to this relation, and for a given shaft the twist is therefore proportional to the twisting moment or torque. According to this relation, we can say that the angle of twist or twisting of shaft, angle of twisting or twisting of shaft is directly proportional to the torque or twisting moment. Okay, according to this equation. In a beam, the bending moment produce a deflection. In the same manner, a torque produced in twisting in the shaft. Okay, means if comparing the shaft with the beam, then the bending moment produce the deflection. Okay, bending moment is produce the deflection in the beam, and similar way if we consider the shaft, then in this manner in the shaft the torque is generating the twisting in shaft. We already know that the quantity Cj, it's here that C into J in the above equation is known as a torsional rigidity. Barabar? Torsional rigidity. The quantity Cj stand for the torque required to produce a twist of 1 radian per unit length of the shaft. So torque required to produce a twist of 1 degree or 1 radian per unit length of shaft. Required twisting produce a twisting of radian, some unit radian to required torque. Okay, it's called the rigidity, torsional rigidity, and it's defined as Cj. Okay, Cj is a quantity Cj is defined the torsional rigidity. Similarly, quantity Ei and in expression of deflection of beam. If we comparing these conditions with the help of with beam, so Ei is a elastic constant. Okay, is the moment of inertia. I is the moment of inertia. So Ei is the similar to the Cj, and it's defined as a rigidity of or flexure rigidity of beam. So in beam is a Ei, and in shaft is a Cj, are most similar. Okay, so Cj upon L is a torsional stiffness. Torsional stiffness is defined by Cj upon L. Torsional stiffness is defined as a Cj upon L, and torsional flexibility is defined by the inverse way, L upon Cj. Okay, torsional stiffness is defined by Cj upon L. C is a rigidity of shaft. Okay, clear?